All right, so yes, they're our usual office hours today. And next process due tomorrow. What do they need to say? There's a, what is this thing about the exam? And maybe they can say a decision. And we don't need to have the exam in this class. I know, Lawrence, this is first exam, but yeah. So, happy September. We'll readjust the grades. Okay. Good news? All right. So, last time we were reviewing this very important concept of the block sphere. And so the block sphere is a geometric way of thinking about the space of quantum states for a two-level system. And the space we're talking about is the space of density matrices. Okay? So that's the space of quantum states. In this case, we're talking about the density matrices associated with two-level systems. So those are the density matrices associated with a spin 1/2 particle. So it has a geometric structure, and that geometric structure is both beautiful and useful, but can also be confusing. Because we're talking about the space of quantum states, but then there's something about physical space, X, Y, and Z. They're kind of mixed up in a somewhat strange way, in that these represent the directions of a spin that's pointing in a certain direction in physical space. But it also represents a state in Hilbert space. And the geometry of this is not exactly the same geometry as the geometry of three-dimensional space. Importantly, is that, for example, states that are antipodal are on opposite sides of the sphere are orthogonal, okay, in Hilbert space. So, you know, we have this general rule. If I wanted to say what is the inner product between two states in Hilbert space associated with spin along two directions, n and n prime, and as we showed last time, that's related to the dot product in this way. Right, so we have the inner product in Hilbert space, and we have the dot product between the directions in physical space. And so importantly, there's this doubling of the angle, right, or halving of the angle depending how you look at it. So states that are at 90 degrees to one another on the block sphere are not orthogonal. In fact, every state on the equator here is a 50-50 superposition of states on the north and south pole, right? Because the problem with that would be a pi over 4, cosine squared of pi over 4 is a half. So every one of these states here has a half probability of being up, or a half probability of being down, as we know, right? And what distinguishes those different states is the relative phase between them, right? So every state on the surface of the sphere is a pure state, and every pure state is some spin along some direction, right? So if I pick a direction as specified by angles theta and phi, then the state corresponding to the spin along that direction can be written with a particular phase convention this way. Okay. The states interior to the sphere are the mixed states. And the degree of mixedness depends on how close I am to the origin. Okay? So every point in this ball is specified by a vector. That vector is the block vector. So there is a one-to-one relationship. You give me the block vector, I can tell you the state, and vice versa. They are related in this way. So every vector in this three-dimensional representation is in one-to-one correspondence with a quantum state, and vice versa. You give me a quantum state for the spin 1/2, and there is a block vector associated with it. And the block vectors associated with the pure states are unit vectors on the surface of the sphere. Okay? And we have all kinds of algebraic relationships here. All kinds of algebraic relations that start with nothing to be at your fingertips. For example, I can write any pure state or a projector onto any direction in terms of the Pauli matrices this way. And importantly then, we can abstract this away from the particular case of a spin and think about an arbitrary two-level quantum system, which is sometimes called the pseudo-spin. But in modern parlance, we call it a qubit. Okay? And we define two orthogonal states, and we take the standard basis. The z basis gives us 0 and 1, and then every state of the qubit is in the block ball, where the surface of the block sphere represents the pure states of the qubit, and the interior represents the mixed states of the qubit, the origin being the completely mixed state with just a 50-50 statistical mixture of 0 and 1, or 50-50 mixture of any two orthogonal states that I like. And often, when the terms x, y, and z become confusing, we forget about x, y, and z, and we just write them as sigma 1, sigma 2, and sigma 3. We'll talk about the one axis of the block sphere, and the two axis of the block sphere, and the three axis of the block sphere. For example, if as you have in your homework, you're talking about polarization of light, you might have one direction as x direction of polarization, the other one is the y direction of polarization. But that may have absolutely nothing to do with what we call sigma x, sigma y, and sigma z. So we don't want to call them that, so we'll call them 1, 2, and 3, and I encourage you to do that for your homework if you haven't done that, because it gets confusing. I mean, you can call them h and v, and then you don't have to worry about x and y, which we sometimes do horizontal and vertical. But often, if we don't want to, if there is a physical x, y, and z, and your block sphere is really a separate abstraction from those directions, you want to get rid of those labels. Okay? All right. Any questions? Yes, sir.
That inner product.
Yes, this thing.
This is only valid for pure states, yeah?
This particular, that's correct. I mean, one can look at a more general question, and I actually encourage you to do that. What is the... So, I can look at the trace inner product. As we discussed, I can look at the trace inner product for two matrices. That's how we take the inner product. Of course, this is a Hermitian matrix, so I don't have to worry about that. Okay, so what is that? Well, I can plug in this relationship. There's a Q and a Q prime, and take the trace, and I will get So that is a general relationship.
Is it 1 plus out of 2?
No, it's exactly that. It's exactly that. Because oh, okay, yes, no, yes, oh, sorry, indeed. I was just looking at one piece, thank you. No, it's exactly this. Just like that. Now, so that's generally true. Now, this is a little bit of a tricky business because there's this notion of fidelity, which is saying something about the overlap between two quantum states. And when we talk about pure states, that's a clear thing. But when you talk about mixed states, it's not quite clear because there's different notions of distance. And there's different, what we call, when you have a notion of distance, you have a measure. There's something, you really want to think about them as probability distributions. There's something called the Burris measure, and there's something called the Ohm fidelity, and blah, blah, blah. This is why I don't usually like to talk about this relation, because it seems to say something about the overlap of the two quantum states, and that might not have the operational meaning we want. So while mathematically it's a true statement, it doesn't really have the operational meaning that we would want. But that's a very subtle point. All right, let's now talk about then. So we talked about the state space. What we want to talk about next is dynamics. So, we're talking about dynamics. The first thing we have to ask is about the Hamiltonian. Okay. Now, we're talking about a two-level quantum system, and as we know, any operator on a two-level quantum system can always be decomposed as some amount of the identity, and some amount of sigma x, some amount of sigma y, and some amount of sigma z. So I can always write this as some amount of the identity plus some amount of the Pauli matrices. This says nothing about the physics. It says nothing. It just says something about the mathematics so far. That just says that any two-level system, that's all you got. And so, of course, the identity part of the Hamiltonian does not affect dynamics in any way, right? Because this is all states would be operated on in the same way. That, in some sense, would affect the overall phase of the quantum state. But as we know, the overall phase of the quantum state is irrelevant, because it has no effect on the probabilities of measuring outcomes, and that's all the quantum state is. So typically, although we might want to, in certain cases, fix what the absolute ground state is so that we know what the energy is relative, we usually don't care about this. So what we see is that the only thing that there is in a and actually, let me write this in a slightly different way because I don't want to confuse it with the physical magnetic field. I'll write it like that. All there is this kind, the Hamiltonian is of this form, which is, the physics of this is a spin 1/2 in a magnetic field. That's the only thing there is. It's It's the only kind of Hamiltonian that we can have for a two-level quantum system, is the dynamics of a spin and magnetic field. Nothing else. There's nothing else it could be. So just to remind us, if we have a spin in a magnetic field, a Hamiltonian, there's a magnetic dipole moment interacting now with the magnetic field. The magnetic field we treat as a classical field for now. And the magnetic dipole moment is proportional to the spin operator through something that's known as the gyromagnetic ratio. So for example, for an electron, as you remember, the gyromagnetic ratio is the G factor of the electron times the Bohr magneton in units of h bar. And of course, it's negative because the electric charge is negative. And this negative sign is one of the banes of our existence of working with these things. Because you got a minus here, and then you got other minus signs. This way, by thinking about the gyromagnetic ratio as negative helps, because we get rid of an extra minus sign that we don't have to take care of. We don't have to worry about it anymore. Because, and then in this case, although I don't have to think about it as an electron, I can just think about the case where the gyromagnetic ratio is negative. The Hamiltonian then takes the form h bar omega naught, I'm sorry, takes the form omega naught dot s, which is h bar omega naught over 2 dot n sigma, where I've chosen omega naught to be equal to minus the gyromagnetic ratio. This is known as the Larmor frequency. Let me call this magnetic field B naught. That's a question. Yes, I'm listening.
So when you define the Hamiltonian above, you have B dotted into the sigma,
Yep.
but then when you're writing the Hamiltonian for the magnetic stuff, you have the reverse orientation, the vector and the matrix on the second line. Yeah.
Yeah, it doesn't matter.
Doesn't
This doesn't matter because this is a number. I could write this as I like, as B dotted into that. These commute,
Okay.
because this is just a number. It's like, which is what I said is a classical magnetic field. It's not an operator.
Okay.
So it doesn't matter in that case. This looks crazy. Just need that B. So that B dot U. I mean, it is, but God, just, this cognitive dissonance. So B dot E versus E dot D, Okay, right there.
I think it makes sense now, though.
Yeah, yeah. All right. So, the Larmor frequency. So let's just remind ourselves quickly. If I looked at the Heisenberg equation of motion, So let's look at the equation of motion for one of the components of spin angular momentum. According to our Heisenberg equations of motion, I get that by commuting this with the Hamiltonian. So if I plug that in, that's that. And now if I write this in repeated index notation, this is the jth component of that, SI, as repeated index summation convention. And this is I h bar epsilon I j k, the spin component sk. And thus, this is equal to epsilon I j k, the j component of that Larmor, times sk, right? And so, what this tells me is that as a vector of matrices or operators, this is equal to omega cross S. Right? Or equivalently, if I asked how the expected value of the spin operator evolves as a function of time, it evolves in this way. Taking the expectation value of both sides of this operator equation, right? And so, what is that equation? That is the equation of a gyroscope. That is a vector S, with the expectation value of S is some vector, will evolve as a function of time by precessing around the axis that is defined by this vector with an angular velocity given by the magnitude of that. So if I have omega naught, some vector, and I have the spin vector, then what it's going to do is it's going to precess around that axis. It's going to precess as a top precesses, like a gyroscope precesses around that axis with an angular velocity given by the magnitude of that and the axis rotation and little right hand rule. Put your chalk down if you're a right when you use the right hand rule, otherwise you use the left hand. That's always bad. All right. So, as we know, if you put a spin in a magnetic field, it will precess around that magnetic field just as a classical top does, with an angular velocity that's given by the Larmor frequency, and this is called Larmor precession in classical mechanics. So a spin just undergoes Larmor precession in the presence of a magnetic field. All right. Now, let's think about this from the point of view of the Schrodinger picture, or at least thinking about quantum states, rather than the expected value of some observables. So if I write again our Hamiltonian, I'll call it H naught, was minus mu dot V naught, which we said was that, right? So now I ask you, what are the eigenvalues and eigenvectors of this Hamiltonian? First of all, what are the eigenvalues? Plus or minus h bar, the magnitude of omega, over omega naught, call that without the vector sign, that, right? And what are the eigenvectors? Of that Hamiltonian? Try it.
Up and down,
Up and down along the direction of omega, right? We know. So this thing has got some magnitude and then some direction. It's the direction of the magnetic field. Let's call it just some axis. So this vector omega naught has some magnitude and some direction, whatever that direction is. And so the eigenvectors of this, so I'm going to have a spin up along that axis and a spin down along that axis. This guy gets shifted up by omega, h bar omega over 2. This guy gets shifted down by h bar omega 2. So the energy difference between those is h bar omega. Okay. Typically we talk about anyway, that's the energy difference between those, right? One goes up and one goes down by h bar omega over 2. All right, so now if I want to drive dynamics of the system, this is what we just discussed there. If I start in a state that's not in an eigenstate, what we're going to get is a Larmor precession. If I started the spin either aligned or anti-aligned with the direction of the magnetic field, well, it's going to do nothing, right? That is, won't precess, and that, from the point of view of the quantum mechanics, corresponds to an eigenstate, a stationary state of the Hamiltonian, right? Now, I could think about now, if I want to drive the system, say I prepare the system, say spin down, and I want to drive it to spin up, what could I do? Well, I can try to apply a magnetic field that is oscillating with time so that the frequency of my oscillator is on resonance or close to it with that transition. And think about this from the point of view of absorption. So I apply some which is oscillating with time. And then if that frequency is tuned to resonance near to omega naught, if it's not resonance, then I expect to be able to absorb some of that energy and jump from here to here, right? So, how would I calculate the probability for it to get there? Well, the typical way one learns about this, at least one used to learn about this, about when thinking about this kind of absorption problem, the first thing you would pull out of your bag of tricks, if I wanted to think about absorption, is Fermi's golden rule. Right? And so you may remember. So in this case, we would say, okay, this thing has some, my interaction Hamiltonian in this case would be time dependent. I'd have some component that was oscillating like e to the minus I omega t, and some component that was oscillating e to the plus I omega t. And the coefficients we would call the positive and negative frequency components. Right? And Fermi's golden rule says that the rate of absorption is related to the matrix element that takes me from the initial state to the final state of the interaction Hamiltonian squared. There's some factors here, like 2 pi over h bar squared, and then something like the density of states. Right? Everyone who's seen it knows it. So, what the heck? Now, Fermi's golden rule is sort of, you know, sort of the standard physicist's tool for thinking about absorption and emission. You have some interaction Hamiltonian with the matrix element that takes you, in this case, from here to here, and then, you know, density of states. How density of states we're talking about here? Well, you know, there's life beyond Fermi's golden rule. Fermi's golden rule actually has very limited applicability. Fermi's golden rule is appropriate when there is a kind of, if I didn't have a single line here, but I had some breadth of lines here and some potential weird processes that make the system incoherent, then I would do all the trickery that usually leads us through time-dependent perturbation theory, integrating to infinity and setting this thing to a delta function and blah-de-blah, and then ultimately end up with Fermi's golden rule. Or I might not have a coherent light source. I might have a mercury lamp that I was shining on the system, and it has some spectral density, and then I have some black body distribution, there's some density of states here. But that's not what we're talking about. We're talking about, I have a 2-level system, there's no density of states, there's one state up there, and I'm talking about one frequency. So what we should do is not think about this incoherent process, we should think about a coherent process whereby the system doesn't absorb and jump from here to here, but evolves continuously in time according to the Schrodinger equation. The Schrodinger equation tells me how the system evolves as a function of time given a Hamiltonian. And this problem we can solve. And so we will. We'll come back as time goes on to understand where the applicability of Fermi's golden rule comes in. Problem. Yes, sir.
Like we can use the density like a delta function for this problem.
No, we can't. That's not really, that's a meaningless, you can write that as a formal statement, but the delta function is only meaningful inside an integral. And that integral is only useful if you have the timescales, as we will see. If there are timescales in the system that are associated with a broad band of either final states or a broad band of the driven system. Otherwise, it's a meaningful state. A delta function is just a mathematical trick. And it only makes sense in an integral, and the integral only makes sense in the incoherent limit. Otherwise, it's meaningless. So let's go back and think about this problem now, solving the time-dependent Schrodinger equation. So, the problem we're going to solve is the following. We're going to put the system in a magnetic field, a strong magnetic field along some direction, a static magnetic field. And that static magnetic field I'll call the parallel. And our goal is to flip the spin. Flip the spin, say, from spin down to spin up, or vice versa. Okay? So, we're going to have to apply a perturbing magnetic field. What direction should we put that magnetic field in if we want to flip it from, say, spin down to spin up? We should put it in the perpendicular direction, right? So we should have some V-perp. Now, if we just applied an extremely strong magnetic field that overwhelmed this, then, ultimately it would flip. But that's not the point here. The point here is to use resonance. So resonance, of course, is an extremely important physical phenomenon. It means that you need some tiny little fly that is just shaking and applies almost no force at all. But if that force is applied in an oscillating way so that it is at resonance, it can have a profound effect. The bridge blows down the Tacoma Bridge, and everyone's seen that in physics, whatever one. So this is going to be a magnetic field that is absolutely tiny in magnitude compared to that. But it's going to be oscillating at a frequency that's resonant with the system, right? So the idea here is, okay, let's say I had a spin that was close to spin down. What would it be doing? Well, it would be processing here around this frequency, around that axis with the Larmor precession, right? And we want to oscillate the system in some way in the XY plane so that it is resonant with this natural frequency of precession. And in doing so, we'll get a resonant effect and the spin will flip. That's called magnetic spin resonance. And it's beyond what's behind the MRI machines, which used to be called nuclear magnetic resonance, but nuclear is a bad word, so we just call it magnetic resonance imaging. All right, so we're talking about spin magnetic resonance here. Our Hamiltonian is going to be time dependent. We have H0, which is the magnetic field associated with the static field. And then we have H interaction, function of time. My H0, we said was minus mu dot V naught, which was H bar omega 0 dot into sigma. And I'm going to choose this axis to be the z-axis. Okay. Actually is z. It's a physical direction in space. Okay. H int is going to be mu dot d perp as a function of t, which I'm going to take to be have an x component and a y component. So it's in the transverse plane, as we said, would make sense in order to torque the spin to flip it. Right? Okay, so with that said, this will be equal to let's see how I want to say this. Yeah, just writing the magnetic dipole moment in terms of the spin and the gyromagnetic ratio. Okay? All right. So now the question I have for you is, if I want to most effectively flip this spin from down to up, how should I choose these components, x and y, as a function of time? Well, the best thing to do is to make this field itself rotate in the xy plane. So then, you know, here I am, I'm the spin, I'm processing. At every point, I would see in my reference frame this transverse field, which isn't moving if it was processing at exactly the same frequency. So if the frequency at which this thing is going around is exactly the same as the natural resonance frequency, omega naught, then in the frame of the spin, it just sees this transverse field and it will torque around it. Is that clear? Because from its point of view, it just sees a magnetic field perpendicular to it, and thus it will torque around. If this magnetic field was moving at its different rate, if it was processing omega, if the magnetic field was rotating around at a different rate, then it wouldn't be as effective. If it was going the other direction, it would really screw it up. It would just get wobble a little bit. It would never have time to go anywhere. So the most effective thing to do is to choose this thing so that the magnetic field is rotating. So we'll choose a rotating magnetic field. Which has some magnitude, and the direction will just rotate in the xy plane with the frequency omega. When omega equals omega naught, we expect resonance. Okay. So this thing now is equal to h bar is something I'm going to call capital omega cosine omega t sigma x plus sine omega t sigma y, where omega here is the Larmor frequency in the transverse direction, okay? Which is known as we will see, the Rabi frequency. After I. Rabi, who is the father of spin magnetic resonance, and basically the godfather of our field. Everyone is related to, you know, he's kind of the Genghis Khan of quantum optics. So everyone's either related to Rabi or Bauer. Everything that was it. I'm related to Rabi. He was my great-great-grandmother or something. All right, so far so good? Okay. So, what we have now, we've looked at this particular problem of, we'll write down the Hamiltonian for a spin in a static magnetic field and a rotating transverse field. So h as a function of time is equal to h bar omega naught over 2. This is the resonance frequency, the natural resonance frequency, plus h bar capital omega, the Rabi frequency, cosine omega t, plus sigma y sine omega t. This is the Rabi frequency. And this is the applied oscillation frequency. Is everyone clear what these three different frequencies are? So this frequency depended on the strength of the static field. This frequency depends on the strength of the applied field. And this frequency is the frequency at which the field is oscillating. Okay? There are three different frequencies. Okay. All right, so now the goal is to solve, so the goal, given the state at time equals 0 is spin down velocity, that's the ground state in the absence of the perturbation, find the state at a later time. How are you going to do it?
We can find the matrix element.
Matrix elements, I can find the matrix on the Hamiltonian, I can do that. You can't answer that.
Do what you did in your notes.
That's not fair either. I have to solve the Schrodinger equation, right? So I have to solve the Schrodinger equation, the time-dependent Schrodinger equation. Now, it's not so trivial to do that in this case, because the Hamiltonian is time-dependent, as we will see. This is confusing. The time dependence here had nothing to do with the Heisenberg picture. It has to do with the fact that we applied a classical field that was time dependent. So in the lab, we turned on the microwave oscillator, or whatever, and it was oscillating at 9.2 gigahertz, or whatever it was oscillating at, and that's why the Hamiltonian is time dependent. Okay. All right, so, we have to solve the time-dependent Schrodinger equation. That is, right? Now, you might say, well, okay, I can write down a formal solution. I know that the state at some later time is given by whatever the unitary time evolution operator is acting on the state at the initial time, right? But what is this in terms of the Hamiltonian? E to the minus E, try again.
You should diagram of that also.
What's that? Yeah, the time order integral.
Yeah.
The problem is that the Hamiltonian at two different times does not commute with one another. So if you look at this in Hamiltonian at time t equals 0, it's along some direction x plus z. But at some later time, the Hamiltonian, say, when this is pi over 2, is along the direction y plus z. And those two operators don't commute. And so you can't do this. You can't even write the integral. What you can do is write a formal thing with a script dt, which is the time-ordered exponential, as Sam suggested correctly. And that is the solution. But that's a formal solution, and there's no way to actually write down a closed form for that. This is the time-ordered exponential. So it's a little bit of a problem. We really can't solve this problem exactly. Or can we? It turns out, in this particular case, we can. Because of the way that I said, if I go into the frame that's co-rotating with the applied magnetic field, then in that reference frame, the Hamiltonian is static. Yay! And if I have a static magnetic field, or static Hamiltonian, then I can just exponentiate the Hamiltonian. So the trick to solving this problem is to go to the rotating frame. So, how do we change a reference frame in quantum mechanics? I mean, we know how to change a frame in terms of classical, we just change the coordinate system, but what does it mean to go to a frame? So, a change of frame means do a unitary transformation corresponding to the transformation.
Won't the new frame always be moving though?
It will. And that's important because there's a kind of fictitious force, as you know, in a co-moving frame. So we have to take that into account. So in the moving frame, there's a kind of fictitious force. But beyond that, all the applied forces are static. So let's do it. Show you how it works formally. So I want to go to the rotating frame. The frame, or let's just say the frame rotating at omega. Okay? That's the applied frequency, not the natural resonance frequency, but the applied frequency, because in that frame, the magnetic field will all appear static. All I'll have is well, you see how it works. So, what unitary transformation does that? This is a rotation around z-axis with angle omega t. That's exactly. So I would say the unitary transformation that accomplishes that, I'll call it the rotating frame unitary, is just a rotation around the z-axis by the angle omega t. So this is some unitary. And so now, going to a change of frame is like going to a different picture. You may remember from your studies in 521 and 522 about the Schrödinger picture, the Heisenberg picture, and the interaction picture. This is a kind of form of the interaction picture, although it's not the interaction picture. It's a close cousin. Okay? The interaction picture you take out the free evolution, that would be an omega naught. But this is not omega naught, this is going to the frame rotation of this. So in this new picture, if I have some operators which are time independent in the Schrodinger picture, in the rotating frame, they're going to be time dependent according to that. Okay. So we've taken some of the time dependence out and put it into the operators in the rotating frame. And then the states in the rotating frame are related to the states in the Schrodinger picture. By taking out that time evolution from the state, because I put it into the operator, such that the expectation value of this is the same as the expectation value in the Schrodinger picture. So we've just taken some of the time evolution out of the state and shoved it onto the operators, the part that corresponds to this rotation. Now there's a trickery to this, which is because the Hamiltonian is time dependent and related to the question that was raised earlier about, but we're in a rotating frame. Isn't there something funny that goes on there? Well, yes, that fictitious force, sometimes known as Larmor's theorem, if you ever learned that in classical mechanics, appears here in the Schrodinger equation as well. Let's see how. So, let's look at how the state evolves in the rotating frame. Well, that is equal to what is that equal to? Well, I take the time derivative of the state in the Schrodinger picture, but I also have to take the time derivative of that transformation according to the product. Now this is the Schrodinger equation. Says that the state evolves according to time, according to the Hamiltonian. This, we have to take the time derivative of that, and that is equal to I omega over 2 sigma z times u dagger. Right? If I take the derivative of this thing with respect to time, I bring down the exponent, take the derivative of the exponent, and I get, actually it's the dagger of that, that's why it's a plus.
Can we say the second term plays the role of fictitious force?
We do, exactly. So we're going to see that in just a moment, absolutely. So that's exactly right. So but before I do that, let me play a little trick here and shove in a u dagger here, and then combine that all together into the following thing. So, what we have here is that the state in the rotating frame evolves according to a Schrodinger equation with a new Hamiltonian. The new Hamiltonian is the unitarily transformed old Hamiltonian, but it has an additional term in it. Right? So let's look at this carefully. In the rotating frame, what we said is that we have to transform the operators according to the unitary transformation corresponding frame. But as was said, there's this additional term here. And look what that additional term is. That additional term is like a fictitious magnetic field. It's like an additional magnetic field in the z direction, but in the minus z direction in this case. And that's known as Larmor's theorem. If I'm in a rotating frame, it's as if the force that I feel as an electron is as if there was a Larmor force on me, a V cross B force on me. So the force in the rotating frame is like an additional fictitious magnetic field. That's something that's well known from classical mechanics, and we see the same thing because this is still physics, even though it's quantum mechanics. Sometimes we forget that, but we shouldn't. All right, Larmor's theorem. Look it up. All right, cool, excellent. So with that said, we have to find what is the new Hamiltonian. Okay. Now firstly, I'm going to come back up here to this thing. You can do it on wherever page you're on, but I can cheat. And I'm going to rewrite sigma x and sigma minus in terms of sigma plus. I'm going to rewrite sigma x and sigma y in terms of sigma plus and sigma minus, right? So this is equal to sigma plus plus sigma minus, right? And this is equal to minus I sigma plus plus I sigma minus. So with that said, this is equal to h bar times the Rabi frequency sigma plus e to the minus I omega t plus sigma minus e to the plus I omega t. Okay. As expected, there is a term that goes like e to the minus I omega t. We call that the positive frequency component. And there's a term that goes like e to the minus I omega t. Now I just realized now that I wanted to make this a slightly more general. So I'm going to make you mad and erase this. I'm going to allow this to have an arbitrary phase. So the phase doesn't have to be 0. Sorry, go back and you know this object. So there's going to be over here an e to the minus I phi, and over here an e to the plus I phi. All right, so that's the Hamiltonian in the Schrödinger picture. What's the Hamiltonian in the rotating frame? Well, we have to apply this unitary transformation to this Hamiltonian. Right? And then we're going to have to subtract off a piece coming from the fictitious magnetic field in the rotating frame. So, to do that, let's do an aside to the aside. I ask you the following question. What is this? Any thoughts on how I might calculate that? So there's lots of ways to think about that. We can be really crazy. We can have a Hausdorff, I don't know, something. But it's trivial. One of our favorite things to say as physicists. If we write this in terms of bras and nets, because then what is this equal to? What happens when this operator acts on this? Sigma z, it's an eigenvector. This is an eigenvector of sigma z with eigenvalue plus 1. So it's e to the plus a. And this is an eigenvalue of with minus 1. So they combine together to give e to the plus I omega z sigma plus. And similarly, so, with that said, we beautifully have that the unitarily transformed Hamiltonian is equal to h bar omega naught over 2 sigma z plus h bar times the Rabi frequency over 2. And look what happens. The time dependence goes away. What a shocker. Because when we put this in, it's going to get the plus and it cancels that. The other one's got a minus, it cancels that. And I get something where the time dependence is gone. As expected in the rotating frame, because we rotated, co-rotated with the field. This one's a minus and this one's a plus. This is static. And thus, we have, importantly, the Hamiltonian in the rotating frame is equal to minus h bar delta over 2 sigma z plus h bar omega over 2 sigma plus e to the I phi plus sigma minus e to the plus I phi, which is equivalent to cos phi sigma x plus sin phi sigma y. Delta is omega minus omega naught, is, as we've said, the detuning. The detuning is the applied frequency minus the resonance frequency. The applied frequency minus, that's our sign convention. Okay, so what we have done by going into the rotating frame is made our Hamiltonian static. And thus we can solve for the time evolution operator without worrying about the time ordering. We can just exponentiate our Hamiltonian as we are wont to do when we write down the time evolution operator. So, what we have then is that a new piece of chalk. The state in the rotating frame at a later time is e to the minus I over h bar. The Hamiltonian in the rotating frame, which is now static, times that at time t equals 0. Because we could just exponentiate it because it was time independent. And that's our Hamiltonian. Now, I ask you, what is this operator? Well, it's the exponentiation of this operator. But I can rewrite this operator in the following way. This operator is equal to h bar times some big vector I'm going to call omega tote over 2 dotted into sigma, where omega tote is equal to something which has the component minus delta in the z direction plus capital omega cos phi sigma, e sub x, plus sine phi e sub y. If I take this vector and dot it into this, I get this. So this is a vector. It has the units of frequency. It has x component omega cosine phi. It has y component omega sine phi. And it has z component minus delta. So, my time evolution equation is that, plugging in for the Hamiltonian. All right. So now I ask you folks, what is this operator? It's a rotation operator. This is an SU2 rotation. In fact, that's all we could possibly have in this system, because the only thing the Hamiltonian we have is proportional to the Pauli's. And when you exponentiate that, you get an SU2 rotation. That's all we got. We can only take spin from one direction to spin in another direction. And that is a rotation operator. There's no other kind of time evolution in the system for a two-level system. It's to take a spin in one direction and move it to another direction. This operator is equal to, so let me write omega tote as having magnitude and a direction. The axis. The magnitude here is the magnitude of that vector, which is the square root of the Rabi frequency plus delta frequency. This is known as the generalized Rabi frequency. And the direction is equal to this over its magnitude, which is minus delta in the z direction plus omega of omega tote cos phi x plus sine phi. So, how do we apply this? Well, we know for any one of these guys, I can always write this with our famous formula for rotation matrices in 2D. We have the cosine of the angle over 2 times the identity minus I sine of the angle over 2 times the Pauli operator in the direction. Is that clear what I just did? Because we said any rotation matrix in 2D has this form. Okay, let's just look at a simple first case. Let's say I'm right on resonance. Let's make delta equal to 0. And for simplicity, let's just set the phase to be 0. All right? So in that case, this term is 0. This term is 0. And then I have just that. So in that case, the state in the rotating frame is equal to cos omega 2 times the identity minus I sine omega t over 2 sigma x. Right. So let's say that at time t equals 0, I started spin down along Z. What do I get? Well, I'm going to get cos omega t over 2 down minus I sine omega t over 2. And what happened when sigma x acted on that? Well, sigma x is equal to sigma plus plus sigma minus. So what is this equal? Spin up. Okay. So we've solved the problem for that specific case. So now, for example, if I ask you what is the probability to be up along time as a function of, up along z as a function of time, what is the answer? Sine squared omega t over 2, which is equal to 1 minus cosine omega t over 2. So if I were to plot this as a function of time, what I would find is the following. The population in the excited state oscillates. And it oscillates with what frequency? Omega. You could have said any omega, they're all true. In this case, the Rabi frequency. The Rabi frequency, which tells me the strength, which was proportional to the strength of the perturbing field, determines the rate at which I go up and down. But notice, this thing doesn't just jump from here to here. It is, the probability distribution is continuously changing. And it oscillates. At some point, it's 100% probability to be in that, and that's when the time is equal to pi over omega. Or said another way, omega t is pi. This is known as a pi pulse. A pi pulse is a pulse of field which takes the state from the ground state to the excited state, rotates it by 90 degrees. Okay? A 2 pi pulse would put it right back. What about a pi over 2 pulse? When omega t is equal to pi over 2, what happens when omega t is pi over 2? So this would be when this omega t is pi over 2. This is cosine pi over 4, which is 1 over root 2. And sine is also 1 over root 2. Which is that, which is equal to minus I up along z plus I down along z over root 2. Which is what?
Y.
Y. This is spin up along y. And in fact, this is exactly what we expect. So let me just draw this last picture before we go on. We have the block sphere, or the block egg, whatever the hell I just drew. Try again. Sort of more sphere-y. We started the spin over here, spin down along z. We applied this torque to the problem in the x direction. Oh, the x direction is out of the board. In the rotating frame, I just see that. What's going to happen? It's going to Larmor process around here. When I stop, when the angle is pi over 2, I'm here, spin y, up along y. And eventually, I get to be spin up along z. And I'm going around the great circle here, driven. Yeah.
Is this spin Y in the rotating frame or in the?
This is in the rotating frame. So you're absolutely right, because this whole thing goes, it's going around the sphere at the big frequency omega equals omega naught. But in the rotating frame, it's y. And that's always true. In every implementation, we always have some resonance. It's always in the rotating frame, which means, and we'll come back to this, when you do an experiment, your key to keeping things coherent is that you have a damn good oscillator in your lab that you're locking everything to. That oscillator might be your, quartz oscillator or whatever it is, then you lock it to something else with some optical frequency synthesis, but you gotta have that, because everything is always locked to some frequency. All right, I did my job. Start getting out of my pants. Got excited. This is fun.